Far beyond the glare of Sol, orbiting a cool K-type star, lies an Earth-sized world with an atmosphere rich in nitrogen and oxygen, and Exo-Earth, whose sky every night can erupt in a celestial ballet of color. Here, the host star's temperament is mercurial. Powerful solar flares and coronal mass ejections, CMEs, buffet the planet with torrents of energetic particles. Under quiet conditions, the planet's magnetic field holds firm, guiding charged particles toward the polar regions where they ignite gentle curtains of green and violet. But when the star's activity surges, the balance shatters, and auroral substorms awaken with feral intensity. It begins with a stellar tantrum. An X-class flare erupts from a sunspot cluster, followed by a CME hurtling at millions of kilometers per hour. 48 hours later, the CME slams into the Exo-Earth's magnetosphere. In an instant, the magnetotail snaps, reconnecting field lines on the night side in a massive explosion of magnetic energy. Charged particles, protons, electrons, and heavier ions flood into the upper atmosphere with such force that they bore channels through previously silent layers of gas. From the planet's dark hemisphere, an observer standing beneath the northern auroral oval would see the sky ignite first, as a diffuse red glow oxygen atoms at high altitudes fluorescing under proton bombardment. Then, cascading down through molecular nitrogen bands, shimmering curtains of emerald and deep purple would unfurl overhead like cosmic drapery. As the substorm intensifies, electrojets race around the poles at thousands of kilometers per hour, twisting the ionosphere into loops of charged gas. Lightning-bright arcs of aurora form dynamic vortices that spiral outward from the magnetic poles, writhing and pulsing in rhythm with fluctuating solar wind pressure. Plasma waves' ultra-low frequency oscillations born in the magnetotail reconnection modulate the aurora's brightness, causing the lights to flicker as if the planet itself were breathing. Simultaneously, radio emissions known as auroral kilometric radiation surge, escaping into space and broadcasting the storm's ferocity across the star system. On the ground, high-latitude seas boil under the electromagnetic onslaught. Magnetic fluctuations induce currents in conductive oceans, stirring up turbulent flows that clatter ships moored in polar harbors. In the upper crust, telluric currents flow through metallic ores, generating geomagnetically induced currents that overload power grids and flicker the glow of city-span lights thousands of kilometers from the poles. But for those who venture into the wilderness and floating platforms tethered near the auroral zone, nothing competes with the spectacle above. The sky becomes a living canvas. Curtains peel back to reveal ghostly rays. Coronas burst like spectral fountains, and patches of pulsating green dance to an otherworldly melody. The substorm peaks in minutes, then slowly subsides. Magnetic reconnection shifts outward, new field lines close, and the particle injection tapers off. The vast auroral ovals shrink back toward the poles, their edges blurring into faint halos before dissolving altogether. In the aftermath, the planet's ionosphere teems with energized particles, launching atmospheric gravity waves that ripple downward into the lower atmosphere, whispered echoes of the storm. Over the following hours, residual currents decay, and the magnetic field relaxes to its pre-storm configuration. Yet the memory of the substorm lingers. Satellites that surveyed the event transmit data on particle fluxes and field perturbations. Ground-based magnetometers record the shift in magnetic latitude. Even long after the lights have dimmed, the planet's climate absorbs subtle heating at high altitudes, influencing weather patterns in twisted, indirect ways. And somewhere, deep in the frozen wastelands beyond the auroral zone, a lone outpost of researchers compiles spectroscopic maps of the storm, cataloging its colors, its temporal evolution, and its role in sculpting the planet's atmosphere. In the grand tapestry of the Exo-Earth's existence, auroral substorms are both terror and wonder, demonstrations of raw stellar power and reminders of the fragile shield of magnetism that makes complex life possible. Under the savage beauty of the dancing lights, one glimpses the intimate interplay between star and planeta cosmic dialogue writ in color, charged particles, and magnetic might. On the fringes of a massive galaxy cluster, where the intracluster medium grows thin and the gravitational tides shallow, a compact group of 4 spiral galaxies drifts toward oblivion. For eons, they have orbited one another in relative harmony, forming a galaxy group bound by mutual gravity but isolated from larger structures. Yet gravity's pull is insistent. As the group plunges into the cluster's deep potential well, a chaotic transformation begins, orchestrating a symphony of collapse that will reshape each galaxy forever. The overture begins at the leading edge of the group's infall. The outermost galaxies feel the cluster's tidal force first. Stars in the spiral arms stretch. Their orbits elongate into tidal tails that trail behind like luminous banners fluttering in an unseen wind. Gas clouds collide at high velocities, hundreds of kilometers per second, triggering bursts of star formation as shock fronts compress cold molecular gas. In the wake of these collisions, bright knots of newborn stars ignite, shining blue and white against the reddened dust lanes they emerged from. The gentle grand design spirals become twisted, distorted. Some arms are pulled outward into ghostly filaments. Others wrap tightly around the core in warped rings. As the group's core crosses the cluster's virial radius, the hot intracluster meteoma, diffuse plasma at tens of millions of Kelvin, engulfs the galaxies. Ram pressure strips away their interstellar gas in a process known as ram pressure stripping. Invisible yet powerful, this wind can sweep away the raw fuel for future stars, leaving behind galaxies that glow only with the light of their existing stellar populations. Gas plumes fan out behind each spiral, forming cometary trails of ionized hydrogen visible in H-alpha emission. In some cases, the stripped gas ignites as it mixes turbulently with the ICM, creating jellyfish galaxies with luminous tentacles stretching tens of kiloparsecs. While the outer spirals suffer these effects, the group's central galaxy, the dynamical anchor, now experiences repeated high-speed encounters with its neighbors. As they pass within a few kiloparsecs of each other, their gravitational fields intermingle, inducing bar instabilities in their disks. Stellar orbits scatter. Inflows of gas feed central supermassive black holes, and active galactic nuclei flare to life, emitting jets and winds that further heat and expel gas. X-ray observations reveal plumes of hot plasma escaping from galactic nuclei, evidence of AGN feedback that compounds the cluster's quenching influence. Yet in this seemingly destructive environment, moments of creation arise. Compressed gas clouds in the tidal bridges between galaxies collapse into massive star cluster snots of star formation, nearly as bright as globular clusters. These young clusters, forged in intergalactic space, will eventually be stripped and dispersed, becoming part of the cluster's diffuse intracluster light. Meanwhile, the group's spiral structure dissolves. Stars freed from their circular orbits form stellar streams that trace arcs around the cluster center. These streams carry the kinematic memory of the original group's motion, mapping the gravitational landscape like ghostly footpaths. As the group penetrates deeper, its identity fades. By the time the last member completes its first passage through the cluster core, all four have lost most of their gas. Their disks have puffed into spheroidal shapes, and their star formation rates have plummeted. They have become lenticular or elliptical remnants, stripped of spiral arms and quenched of new stars. The cluster gains new members. The group dissolves into the larger population, its galaxies assimilated into the cluster's gravitational orchestra. Over the next billion years, the cluster's tidal field and the ICM continue to shape these galaxies. They lose dark matter halos through tidal stripping. Their stellar halos merge into the cluster's diffuse light, and their once spiral cores settle into the smooth profiles of cluster ellipticals. The initial substructure of the group is erased, its individual histories swallowed by the cluster's evolving tapestry. Yet even as they vanish, the echoes of their collapse remain. Deep imaging of the cluster reveals faint tidal streams, ghostly arcs of stars stretching across hundreds of kiloparsecs. X-ray maps show cavities where AGN jets once punched through the ICM. Spectroscopic surveys identify pockets of intermediate-age star clusters that trace the group's final bursts of star formation. In this way, the cluster archives the symphony of the group's demise, a movement built from tides, shocks, and magnetic fields, resolved in cold gas plumes and stellar streams, scored across space and billions of years. Thus, the tale of the collapsing galaxy group becomes a microcosm of cosmic evolution. Structures forming in isolation, driven together by gravity, reshaped by environment, and ultimately subsumed, a testament to the relentless, creative destruction that builds the universe's grandest assemblies.